Hello, and welcome to Physics 12, Dynamics Lesson 5, Tension and Dynamic Systems. Today we're going to add one more force, and then put everything together and start to create our systems. The last force we need to look at is tension. Tension is simply a word that describes when an object is being pulled tight. The antonym of tension is slack, or the opposite of tension is slack. Any rope that is under tension spreads its force along the entire length. At every point of that rope, the tension force is going to be the same. That means the tension force is applied to both ends of the rope. If you pull one end with 5 newtons, then the other end of the rope will also feel 5 newtons. Since the tension force is evenly distributed along the entire rope, this is useful for turning the direction of a force with a pulley. By using a pulley, you can change your force of pulling something north into something pulling east. With an ideal pulley, there is no loss of force. Of course, in real life, the pulley itself will have friction, and you have to fight that as well. But for Physics 12, we will assume we have ideal pulleys. This is a very simple idea, and in fact does not introduce any new equations, just changes some questions that we may have. The main uses for tension is to be able to extend your force to affect something farther away from you, and also to change the direction of your force. So here, let's try a question. If you pull with 10 newtons backwards on a rope attached to a pulley holding up a 1.5 kilogram box, what is the acceleration of the box? Now normally this would be a very simple question, but with a rope and a pulley, it changes how our forces work slightly. Normally, if you have your box and you pull on it 10 newtons backwards, then your free body diagram will look like this, with the applied force, gravity, and your normal force. But in this case, we have a pulley that is changing the direction of your force. So in this question, we have our box attached to a pulley being pulled with a rope 10 newtons backwards. What this does is it changes your free body diagram so that this force of 10 newtons backwards is actually pulling up on the box with the same magnitude, just a different direction. On this box, we also have our gravity pulling it down. This question says that the pulley is holding this box up, so we can assume that it is off the ground, therefore there are no other forces acting on this box. So here, we will write down everything that we know. Our applied force, which is normally 10 newtons backwards, is now actually 10 newtons up because of our pulley. We also have our mass is 1.5 kilograms, and we wish to find the acceleration of this object. So we know our net force is equal to our applied force, which is pulling up, minus our force of gravity, which is pulling down. Here we will say F net is positive, so we will assume it is moving up. If it's actually moving down, then we'll get a negative answer. That's okay. If we get a positive answer, that means we were right and it's moving up. We can change the direction at the end. Now that we've set up our question, we've changed this from a physics problem into a simple math problem. So let's solve for mg. Here we know F net is ma, which is equal to our applied force, which we know, minus mg. We wish to find a. A is equal to Fa minus mg over m. And this is equal to 10 minus 1.5 times 9.8 divided by 1.5. And our final answer is negative 3.13 repeating. Here we see this is a negative sign, so our assumption that it was up was wrong. So this is actually going to be 3.1 meters per second squared down. So simply, tension does not make the question more difficult. It just adds one extra step so you know which direction the force is actually going to be. So you must check the direction of the force after the pulley acting on the actual object. And if we do all of that, we will get 3.1 meters per second squared down. So here, let's try another question. What is the acceleration of a 10 kilogram box being pulled on by a rope with 50 newtons at 40 degrees above horizontal if the coefficient of kinetic friction is 0.20? Here, for this question, we do not have any pulleys, we just have a rope involved that is pulling at some angle. So here, like with any other question, we will start by drawing a picture. We have our 10 kilogram box being pulled by a rope at 50 newtons, 40 degrees above horizontal. We know our coefficient is 0.2, and we don't have any other parts of this question, so we will write down everything that we know. We know our applied force is 50 newtons. We know our angle is 40 degrees. Our mass is 10 kilograms, and our coefficient is 0.2. From the question, we can see that we want to find our acceleration. Next, this is a force question. So like with all force questions, we'll draw a free body diagram. We have our applied force pulling on an angle. We have our gravitational force pulling down, our normal force pulling up, and friction pulling us back. Here, our applied force is on an angle, which is difficult to do at once, so we will divide it into our two components. So we will take our FA and divide it into our FAX and FAY. This angle is 40 degrees, so FAY is FA sine 40 degrees, and FAX is FA cos 40 degrees, or in general, cos theta and sine theta. So we know we wish to find the acceleration. Our first step is to look at our y force. Now in these questions, the first thing you need to check is to compare your FAY with your FG. If FAY is actually greater than your gravitational force, then this object will actually lift up off of the ground and you will have no normal force, which means you will have no friction. So just in case, we need to check to make sure this box stays on the ground. So to do that, we just calculate 50 times sine 40 degrees and 10 kilograms times 9.8. 50 times sine 40 is approximately 32 newtons, and 10 times 9.8 is 98 newtons. We see gravity is bigger than our applied force, so this object will stay on the ground, and we can continue with our question. If the y component of this applied force was actually larger than gravity, then we would have no normal force, no friction force, and your object would actually only have two forces applying on it, the applied force and gravity. And that would make the acceleration at an upwards angle, and it would actually be an easier question. However, that is not the case. So we have our total net force in the y is equal to 0 because normal force will make up for the rest of this gravity. Here, this is equal to our Fn plus our Fay minus our Fg. So our Fn is Fg minus Fay. We wish to find the acceleration in the x, so our F net of x is equal to our ma, which is equal to Fax minus the force of friction. So ma is equal to Fa times cosine of theta minus mu times mg minus Fa sine theta. And solving for our acceleration, we find this is equal to Fa cosine theta minus mu times mg minus Fa sine theta, all divided by m. Putting these numbers into your calculator, you should get 2.513 meters per second squared. So our final answer is 2.5 meters per second squared forward. Since there's no direction in the question, but we know acceleration is a vector, we can just create a direction and we'll call it forward for now. So as you can see, tension force does not really complicate the question. It just adds the ability to change the direction of a certain force, but it's simply just extending the area that you can pull things. So far we have looked at one object at a time, but in real life, nothing is in isolation. So what if we have a system of more than one object? A system is simply any collection of objects. You can decide what is in your system and what is outside of your system. A system can be as simple as the inside of a water bottle, which is just water, or as complicated as the entire planet. Any group of objects that you decide that you're going to work with is considered your system. Imagine you have a line of boxes that are attached with ropes. How could you find the force on each of these boxes? So here, these two boxes are attached together. If this object is moved towards the right, this 10 kilogram box will follow it. Here, you are pulling on this 15 kilogram box with 90 newtons. You are not directly pulling on this 10 kilogram box. But here, a rope attached between 10 and 15 is acting as a second tension force that is pulling the 10 kilogram box along. Here, you are effectively pulling 25 kilograms with 90 newtons. Well, we know the forces on these boxes are different. Since they're different mass, they're going to have a different portion of your 90 newtons. They also have different frictions on the bottom. Since everything is different, is there any way for us to jump from one system to the other? There is one number that is consistent through all systems. That one number is our acceleration. If this 15 kilogram box speeds up forward at 0.5 meters per second squared, this 10 kilogram box must always be the same speed and the same acceleration. So no matter what system you choose here, the acceleration must be the same. Here we have three choices for our system since there are two objects. Our first option, we can say our system is simply this 15 kilogram box. Our second option, we can say the system is this 10 kilogram box. And for our third option, we can say that the system is both the 10 and the 15 kilogram box. No matter which system we choose, the acceleration must be the same. Because these objects are attached together, their motion are aligned. So the acceleration is always the same no matter which part of this object you're looking at. The entire system will move together. We can take advantage of the fact that the accelerations are the same to be able to solve for this entire system by choosing systems in which only one unknown is present at any given time. When we have a system, any internal force is going to be canceled out by itself. For example, if we choose our system to be the 10 kilogram and 15 kilogram boxes, here our tension will cancel itself out. If we look at our 10 kilogram box and our 15 kilogram box, tension is pulling the 10 kilogram box towards the right. It is also pulling the 15 kilogram box towards the left. If we write down all the forces acting on this object, we see for our x direction, we have our 90 newtons pulling to the right. We have our friction force of the 15 pulling to the left. We have our friction force of the 10 pulling to the left. And here we have our tension force pulling to the right, so it is positive. But we also have our tension force pulling to the left, so it's negative. Here we have T2 minus T2, and these will just simply cancel out. Similarly, all internal forces which apply on both sides of an object are going to cancel out. Here, this 90 Newton force is an external force because only one end is being pulled into something in our system. The other end is something outside of our system. Both of these friction forces are external forces because they act between this box and the ground. The box is part of our system, but the ground is not. So therefore, this friction force and this friction force are external forces. However, this tension is an internal force. It pulls right on the 10 kilogram box and left on the 15 kilogram box. So for the system of these two boxes, tension cancels itself out. So using all of that information there, let's try to solve this question. Here, we want to find the force on each box. We already know the first force, 90 newtons, so simply all we're trying to find is our second tension. We will quickly redraw the picture just so we have something that we can work with on our paper. We have 90 newtons pulling forward, and here we are given our forces of friction, 10 newtons and 15 newtons. Our first step is to find acceleration. The reason why we want to find acceleration first whenever we have these dynamic systems is because this is the only number that is the same throughout any system that we choose. This will allow us to jump from one system to the next and have one number that will follow us around. So first, we will find our acceleration. To do this, we need to find a system that has only external forces that we know. If we choose 10 kilograms as our system, then we will have our friction force that we know, but we will also have T2 that we do not know. Since we don't know T2 and we don't know the acceleration, we will have two unknowns in our system and we cannot solve for anything. Similarly, if we choose our 15 kilogram box as our system, we will have 90 newtons forward, which we know, 15 back, which we know, but we have our tension force pulling back that we do not know, and we cannot solve for A because again, we have two unknowns in our system. So we will look at our third option, choosing both 10 and 15 kilograms as our system. Here we have 90 newtons pulling forward, 15 pulling backwards, 10 pulling backwards, and we also have our T2. But in this case, T2 is an internal force. So it is pulling forwards on the 10, but backwards on the 15. So these will cancel out, and we will have one unknown, which is our acceleration. So we will start with our system of both boxes. Here we know our net force can be broken down into our X and our Y. In this situation, we can assume that our net force in the Y direction is equal to 0 because it is not moving up or down. Or in other words, the normal force of our 15 box is equal to the gravity of the 15 box, and the normal force of the 10 box is equal to the gravity of the 10 box. Since in this system we have both Fn and Fg of both boxes, our Fy's will cancel to 0. So to find our total acceleration, we only look at our X. Our net force Ma is going to be equal to our applied force minus the force of friction of our 15 box minus the force of friction of our 10 box. So our acceleration is simply 90 minus 15 minus 10 divided by the total mass of the system. And our total mass of this system is 25. So in this situation, our acceleration is therefore equal to 2.6 meters per second squared forwards. Now we know the acceleration of this system, we can jump to any other system and solve for our remaining forces. The only force we are missing is our tension force. So now we need to select a system where the tension force is an external force. If we try to use the same system with both of our boxes to solve for T2, we could never solve for it because T2 always cancels itself out and we will never have it in any of our equations. At this point, it does not matter which system you choose because either will give you the same answer. So let's try both. First, we will look at our system with the 15 kilogram box. Here we know our net force is equal to our F net in the X plus our F net in the Y. As before, we know our normal force cancels out with our gravity, so this is equal to 0, and we are left with just the X. The F net of our system is M times A, which is equal to the applied force minus the force of friction on the 15 box minus this tension force. Therefore, our tension force is equal to our applied force minus our friction minus mass times acceleration. And putting in our numbers, this is equal to 90 minus 15 minus our mass of this system is now 15 kilograms times 2.6. Putting these numbers into our calculator, we find this is equal to 36 newtons. As I said before, we can do the same thing with our 10 kilogram box. So again, this F net is equal to our X plus our Y. And as before, our normal force we know cancels out gravity, so our net force in the Y is equal to 0. As before, we have our acceleration and times our mass is equal to the tension force pulling this object forward minus the friction force of our 10 kilogram box. So solving for our tension, this tension force is equal to our mass times acceleration plus the force of our friction. Now the mass of this system is equal to 10 kilograms times 2.6 plus the force of friction is 10 newtons, and this is equal to 26 plus 10, which is 36 newtons. The same answer as we got before. So here you can see that the tension force is the same no matter which system you choose. You may have noticed that this second option was actually slightly easier than the first because here we only had two forces acting on the system, tension and friction, whereas earlier we had three forces, tension, friction, and our applied force. As you do more questions, you will start to see which systems are easier to choose, but at the beginning, it doesn't really matter which one you choose, as any will give you the same answer in the end, as we have shown here. So the trick to these questions is knowing which systems to use and which systems that you can cancel out internal forces and have known external forces. The most useful number with dynamic systems is always acceleration. So if you do not know acceleration, trying to find it should be your first step. To find the acceleration, you need to have a system where you know all of the forces acting on that system. So you can do this by choosing a system that ignores unknown forces or fully contains unknown forces so they cancel itself out. For now, practice choosing systems and knowing which systems are good for what situation. Ideally, you will have at most only one unknown at a time, and our first unknown we want to solve is always acceleration. This is all for tension and simple dynamic systems. Thank you for watching.